Sorry. Hey, this is part 2. Sorry that it cut out before. I really can't do anything about it. I just have to go super fast. So we're gonna just add on to this. Not gonna be a lot of talking. Gonna be more like me just getting it on the paper because I know how to do it. My phone just really wants to be a jerk to me so that I can't get any bonus points. Yay! This is connected to C. Connected to O. Connected to O. Connected to H. This is 2. This has got some lone pairs. And this one has some more lone pairs. And this one has no lone pairs because that's already 4. And this one has some lone pairs. And this goes here. And then you have your conjugate base, Lewis structure. I draw a minus already on this one. Oh, and this one's fun because this has a resonance structure. We can already tell because it has 3, whatchamacallits, molecules, atoms, whatever. And this is the minus. We get our O back, we get our O back, we get our C, we get our O. Didn't mean for this to be a little sideways, but I want to have enough space for this O. Shmoop. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yippee-ki-yay. And this part is negative, because that's where it donated to. Okay, we'll draw the resonance structure later. So, oxygen, as this is the donator, same size. Oxygen equal. But we look at electronegativity. Oxygen has the same electronegativity as oxygen, but we look at it in the neighbors, like I said before. Oxygen may have the same electronegativity, but nitrogen and carbon do not. And if we look on our periodic table, we can see that nitrogen is further to the right than carbon is, which makes it more electronegative, which means that O attached to N has more electronegativity than O with carbon. Yay! Which is already part of the solution. But we also have one resonance structure. So, that has an E. We will draw that very fast. And not really explain it. We're just gonna draw it because I think it's self-explanatory, and the side that this is on can switch to the other side. It's so fancy. Oops, I meant to draw this with the double bond. That's what makes it so friggin' fancy. It can switch to whatever side it wants because it's super cool. It has this, and it can go from that to here. Yay! And that means it'll turn from that into... Oh no, I don't know why I drew that like that. No, yes I do. We're just gonna leave those as single bonds right now while I draw this. No, I didn't mean to draw these. Maybe I did. No, I didn't. I did not. And this was supposed to have some other electrons on it. That's why I was confused. Okay, now they're balanced. Jesus, sorry. I got all confused and flustered. And since we're moving this along this, you're gonna end up with your multiple electrons over here because this side is more negative. And this balances out with the bond. So there's not supposed to be any there. Yay! Now it's balanced. It goes back and forth. It's super fancy. Your resonance structure. And a resonance structure means it's way more stable, and that's what we're measuring. We're measuring instability. So that's super important. And because this one is so much more stable than this one, it has more acidic levels. So the H attached to HNO2 is more stable and therefore more acidic than H attached to HCO3 minus. Sorry, H3OC minus, you're not cool. Alright, we're getting down here. I don't know why I drew it smaller, don't worry about it, it's capital. We're gonna go with the conjugate bases. Yay! And they're all conjugate bases. I didn't explain this before. They're all conjugate bases because they're all acids to begin with. Yay! Isn't that such a fun fact? Sorry, I'm real saucy. I'm in a mood right now because my phone will not give me the time of day. Alright, and now we count up our electrons. 1 plus 6 times 4 plus that 1 gives us 32, E negative. 1 plus 6 times 3 plus 1 is 26, E negative. Alright, and then we draw our Lewis structures. One more time. I don't know. I think drawing Lewis structures is pretty easy as long as you can figure out what's supposed to go in the middle. You can figure everything else out. Though I guess that's part of why it's hard for people. And we're lucky that neither of these have resonance structures, because that would make this a little trickier. Well, it would make it easier to determine, but a little trickier in the long run for me to draw. Count them out, baby. Those are all of your lone pairs. And they both donate, surprise, surprise, to oxygen. Now we go to our conjugate bases. Let's do this. O, S, O, O. Double pair. Sorry if you can hear me breathing. I'm very stuffy, so I'm mouth breathing. Please don't dock points for this commentary. I know it's weird. Boom. Oops. See, this is why I make weird commentary, because otherwise it's me drawing dots in silence, and that's pretty boring, I think, and this is supposed to be an explanation, but I don't really know how to explain it because I've already done it twice. Yay! Here's our conjugate base Lewis structures. Now, they both donate to oxygen, so it's oxygen versus oxygen. Again, and that's a cute little face that you draw with that. They're the same size. Boom. So they're equal in that department. The electronegativity. We can obviously say the electronegativity of oxygen and oxygen are the same, and their neighbors are the same. Sulfur and sulfur. Pretty easy, right? Well, there's more of them. That means the electronegativity is greater. More neighbors equals more electronegativity. So more equals greater electronegativity. And that's a big one for stability. And your distribution of your electrons when you have more is better. So you have more stability. Yay! So, distribution just ignore me misspelling all the words this time. Stability. No, I think that's right. Oh well, if it's not, whatever. Resonance structures. None. No. Same size. electronegativity. No resonance structures. So now we can figure it out. Because the oxygen attached to SO4 has a greater electronegativity due to the number of them, and has more distribution due to the number, which is greater stability, the O in SO4 has greater stability, which means that, therefore, the H attached to H of HSO4 minus is more acidic than the H attached to HSO3 minus. Boom. Because you have less things, there's less distribution, less electronegativity, you're less stable. Alright, thank you for watching.